It's okay. Okay, so I'm going to start by the structured meshing. And what you can see here, it's a hydraulic turbine, a Francis turbine. And we have the 3D view. This is the Omnis program that we have for generating meshes in NumIbérica. And you can see initially here, you can see these are the guide vanes. And if we see from the bottom, you can see the runner blades. So we want to mesh this geometry. Okay, so the first thing, of course, it could be to import the geometry and set what is the hub and set what is the shroud and the blades, but that's done already. So we're going to focus on how to tell the measure, how to guide the measure, because it is really automatic, the process, but you have to guide it a little bit and have to give him some hints. Okay, so the first thing would be to set the type of turbo machine that we are going to mesh. So for that, here we have imported the guide vane, the runner, you see. So if we click in the guide vane, here you see that we have a row type, and we can select between very different things. So we have from wind turbines to a centrifugal pump or a compressor. In this case, it's a Francis turbine, so that's what we have to set. And then here you see periodicity, which is set 24 because we have 24 blades on the guide vanes. And here I have to mention that we're only going to mesh one passage. So if you see here, I'm going to maximize again the view. Here you see 360 degrees, you see the whole turbine. But in reality, we're working only with one passage. Okay, and if I show the mesh that is already generated, so it's going to be more clear. It's only one passage that we have, and but we use it to model the whole turbine, as you can see here. Okay, so going back here to guide vane, we set the periodicity 24. I said the row type it's either stator or rotor. Flow path number. So what is the flow paths are on this view, which is the meridional view. So it's cut by a meridional plane of the turbine. You see these red lines that go from the inlet to the outlet. So what I'm setting here is just the number of these lines. So if I set more lines, so I'm going to have more resolution. And if I set less, I will have less. And then finally, we have to set the cell width at the walls. That is what Rémi was talking about, that depending on the Y plus that you target, if you're working with a low Reynolds turbulence model or high Reynolds turbulence model, you will define the cell width. In this case, it's 0.1 millimeters. And it's just that, really. We apply the wizard to this row. And you see here, well, you see some overlapping because I generated only the guide vane, but if I generate the runner too, which I put periodicity 13 in this case, the runner has periodicity 13, the flow path number has to be the same, and the cell width the same, of course, and I apply the wizard to this row. And now we don't see overlapping anymore. Okay, so we can play with the grid refinement level. So if I go to the guide vane, if I want less refinements, I just decrease this number and I apply the wizard again. And you see that right now we have much less refinement, but let's leave it in 14, I think it was. Or even a little bit more. Yes. Okay. So we have more control than this. This is just a wizard. It's very, very simple. But we can actually control the structure of the mesh. So as Rémi was saying, this is based in different blocks. And here you can see the block structure on the left. And we could modify the topology. But for example, what I'm going to want to do here is, I think I have too many cells on the close to the blade. So I'm just going to reduce that and see how that looks like. So you see, it's very easy to modify those parameters. And the same for the runner. We're going to reduce this number and we're going to regenerate again. Okay, this view, the blade-to-blade view, it's the view that you would see if you saw these red lines, okay, the flow paths. So if you look them from the side, you would see this blade-to-blade view. So you can see on the left the guide vane, and on the right side you see the runner. Okay. So that's for this. I saw the block structure. So let's run the mesh. Let's run the mesh. Okay. Start mesh generation. And let's see what happens. Shouldn't take very long. It's performing different steps to generate the 3D mesh. And it should be done in a moment. So here you can see some controls, like for example, for this case is not useful, but if instead of a Francis turbine, we would be meshing a Kaplan turbine, maybe we would like to add a gap at the tip, like at the shaft, and we can do that very easily just by clicking here and then you select the width of the gap. And the same in the half, we could do the same. Okay, so the mesh is generated, and now we're going to check the mesh quality. And we see that we have some cells here that are not very good because we have a minimum orthogonality of 6 degrees. So we're gonna see where we have these cells. Okay, for that we're going to create a mesh quality field of equiangular skewness. We create a cell range, and we are going to do it from 0.8 to 1. Okay, we start the mesh analysis and we compute. Okay, so we have 5,000 cells that are within that range. So what we need to see is where are these cells. So I'm going to deactivate the repetition in order to visualize these cells. And you see that they are suspiciously, all of them are close to the half. So let's see how that looks like. It seems that the cells are not aligned with the flow in the radial direction. So how do we sort this out? This is very common thing in Francis Runner. So we will have to slightly modify the topology, but not the blade-to-blade topology as we were modifying before. We're going to modify the meridional topology, and we're going to add a meridional line for that. Okay, so just add meridional control line, and I'm going to add it from here to there, and now I'm going to modify it. I'm going to bring it a little bit closer there. Okay, and now we regenerate again. So I stop this because it was the mesh analysis, and we overwrite the mesh. So this meridional line, what it does is that it effectively creates a new block separating the runner from the region that is closer to the outlet. So that way, those bad cells that we were having closer to the outlet on the hub won't appear anymore, we'll see. Okay, so the mesh is generated, and we're gonna check again. And now you see that the minimum orthogonality is 26 degrees instead of 5 degrees that we had before. We can also see very easily the distribution of the orthogonality in the cells, and we see that most of the cells are very close to perfect orthogonality, and only a few of them have lower angles of orthogonality, and the same for expansion ratio and aspect ratio. These histograms are very useful to check the quality of the mesh. We could also visualize we could create, for example, a contour of the skewness, and I have to select the mesh there. And this way you will be able to see where are the cells that have less. Okay, sorry. Just there. So you're able to see where are the cells that have higher skewness, which is equivalent to lower orthogonality. And you see that, of course, where you have the surface and when there is a transition, that's where you're going to have a lower quality, but still the quality of the mesh it's really good. And we can show again the repetition. Okay, so this is for structured meshing. And now I'm going to move on to unstructured meshing. And what we're going to do is we're going to mesh a draft tube. So this will be after the turbine. There will be this draft tube. And the first thing again will be importing the geometry, which it's already done, but it's pretty simple. It's just you just import. You're careful with the triangulation. You perhaps specify a maximum size for the triangles, and also ensure that all the regions that have curvature have enough triangles so that they are captured well with good resolution on the tessellation. Because if they are not captured well with the tessellation, then they won't be with the mesh. no way. Okay, so one of the things Remy was talking about meshing, about the geometry when you mesh is that you must have a clean geometry, and sometimes you don't have a clean geometry for different reasons, so you have to clean it up. In Omnis, you have some tools to do that. So you could close holes, for example. You can create an extrusion. You can perform Boolean operations. You can create new primitives like cube, sphere, or cylinder, and you can play with that. So it lets you modify the geometry. However, it must be in CAD format, because if it's already STL, then the CAD information is lost. So it must be CAD format. So in this case, I'm just going to show you how to do a extrusion. Very simple. So you click here on extrude entity. Of course, we have to select the entity before. And you can specify the offset that you want. You just click apply, and you have extrusion of the geometry. So that's it. It's very, very simple. But for this case, we're going to work with the original geometry. And you will have to create different selections to impose different boundary conditions. So, for example, this is the inlet, this is the outlet, and then the rest are walls. But they are separated in different patches because I want to apply different refinements on them. And finally, you can create, for example, a cylinder. I will show you, although it's already generated there. But if I click here on the cone, I can create a cylinder, and it's adapted to that geometry. I'll just have to modify the axis so that it goes in the direction that I want. And why I would want to create a cylinder? It's because I want to apply a volumetric refinement. So I could apply refinement on the patches, but if I want to apply refinement on a bigger region, then patches are not enough. So I need to define a volumetric region and apply a volumetric refinement there. So that's what we're going to do. So after you're happy with the geometry, we would move to domain. And here, the only thing that we will do really is just to set what are the boundary conditions, which for meshing is not very important, but in this program, as you can see, you can continue to simulation. So if you set here what is inlet, what is outlet, it will help you. So I said inlet, outlet, and this is very important, is the seed point. So the procedure that the mesh is generated with Omnis Express is it starts with an initial mesh. Rémi explained, but just briefly, it starts with an initial mesh, and then depending on the different parameters that are applied on the walls, there will be that initial mesh will be adapted and will be refined in that region, and then the vertices are snapped and optimized so that we don't have negative cells. So what we're doing here is we are specifying where the initial mesh is starting, and in this case we just have to make sure that it's inside the domain that we're going to mesh. And it sounds very very stupid, but sometimes you don't realize and it's out, and you try to generate the mesh and you don't know what was the problem. But okay, so that's done. We ensure it's inside, no problem. And then we move to mesh. And what we can see in mesh? Well, we have global parameters, we have local parameters, and we have volumetric parameters if we want to apply volumetric refinement. So starting by the global parameters, our mesh, we want it to be hexa dominant. So we don't mind that we have prisms in between the hexahedrals, but we could generate a full hexa mesh in case we didn't mind that the mesh was non-conformal in between the layers of different size cells. We can specify the initial mesh type. So for this case, it makes sense that it is a Cartesian mesh, but it could be cylindrical if we wanted to mesh the turbine that I was showing you before. Although for that turbine, it makes sense to use Omnis Autogrid more than Omnis Express. And the initial cell size. So this is the cell size of the initial mesh. And from this size, we start refining. For that, we go to local refinement parameters. So for example, at the cone, I show you, I have applied a refinement level of 4. That means that the initial cell of the initial mesh, it's refined 4 times. So it is split in two. The edge of that cell is split twice for it's split in two for 4 times, so that you divide by 16 the size of the edge of the mesh. Okay. You also want to specify the viscous layers on the local refinement on the local parameters. You want to specify the viscous layers if it's a solid, of course. If it's the inlet, you won't have viscous layers. And how you do that? You can switch between different methods. So you have inflation, extrusion, and deformation that Remy was showing you. In this case, inflation is the one that we're going to use, and we specify the first layer thickness that is going to be dependent on the Y plus that you're targeting, and the stretching ratio, which 1.2, it's very smooth from one layer to the next layer. And finally, we specify the number of layers. So we put a target, and then we put a minimum and a maximum. And Omnis Express will calculate which is the best, so that the transition is very smooth. So finally, we move on to volumetric refinement. I show the cylinder here. And we're going to impose a refinement level of 4, which is the same that we were having in the cone. And the diffusion, this we have for local refinement also. The diffusion is just how it's going to be the transition between a refined area and an area that is not refined. So if we increase this number, there will be a smoother transition. But of course, you will spend more cells in that area. Okay, so just one more thing before generating the mesh. Here you can see a preview of the mesh. I don't know if you realize already, but for example, if I go to cone and I change the local refinement to 3, then automatically you will see how the mesh will look like. Of course, it's not perfect because it's only a preview, but it gives you a very good idea if you're going to need more refinement in some areas. Okay, so I'm going to launch the mesh generation. This will take a little bit more of time, because of course an structured mesh it's more difficult for the computer. It will need much more computations to optimize the mesh, not have negative cells, and it's there is much more work for the computer. Okay, while this is working, I can perhaps show you some things here. You can toggle between orthographic and perspective camera. So we had the orthographic camera, and this is perspective. You could create a cutting plane, but in this case, we are only going to cut the geometry because the mesh is being generated, and you can specify, for example, we want it to be perpendicular to Y. We want to flip it. This is, I will show you when the mesh is generated, and you will see, you will be able to spec the mesh inside. And then, of course, you can measure distances. This is useful. Sometimes it's very useful for being able to measure things directly, or you can even create a box just to show all the dimensions at once. I don't know if I have the mesh already there, if I will be able to show it. I think I can't because it's running. But well, it's 80%. There are more complicated parameters that I haven't mentioned. That, for example, here you could activate curvature refinement, that it will automatically detect where there is a curved region, and it will apply refinement there. So you specify the divisions for the curvature. This is like says the maximum number of divisions on an equivalent 90 degrees sphere, and just also specify a minimum cell size so that you don't end up with a massive mesh that collapses your cluster, your computer. Also, you could apply thin walls that Rémi was explaining this. So for example, if you have a heat exchanger and you have two different fluids, so one is inside the pipe and the other one is outside, you want to be able to model the wall perfectly with your mesh. And for that, you would apply this, you would click here on thin wall. You would click on that wall, and you will apply thin wall here. Okay, so the mesh is almost. Another method of refinement, it's proximity refinement. And this is very useful when you have walls that are very close to each other and you want to be able to capture the mesh in between. You would use this refinement method. So it will ensure that the cells that there is at least one cell in between those walls. So for example, especially for this kind of meshing algorithm, which is a volume to surface, is very important because it starts from a seed point and then it grows and it has to pass through whatever passage there is. And if there is a bottleneck, you need to have either a proximity refinement or a local refinement applied there. Otherwise, the mesh won't pass through the bottleneck. Okay, so the mesh is done. We can check the mesh quality. And we see that we have a maximum squeakiness of 0.79, which is it's very good. The expansion ratio is a bit high, but well, we could potentially improve that, iterating more, perhaps applying more refinement or modifying the viscous layers. And here we can show the histogram also, and we can play with the number of bars. So we see that most of the cells have very low equiangular squeakiness, which is great, and just a few of them have more skewness. And I will show you the cutting plane. So I'm going to activate the mesh analysis. And there you can see the mesh inside. We could move this cutting plane so that we are able to see different layers. I think I have there. Okay, so that's all from my side. I hope that you enjoyed this demonstration, and if you have any questions, feel free to ask.